In this episode, we are going to get hands-on with language models. Let's get started. So in all of the other LLM Chronicles labs, we've typically taken whatever technology we discussed in the theory episode and implemented it from scratch. However, for language models, I do not want to do that because other people have already done that a lot of times and much better than I could do it. So instead, I want to point you to two resources which I think you're going to find particularly useful if you're interested in actually building your own language models from scratch. Now, the first resource here is a YouTube video by Andrei Karpathy, and he basically walks you through how to build GPT from scratch, step by step. This is going to be a fairly small model. If I remember correctly, I looked at this video months ago, probably 1 year ago. He builds a character-based language model instead of building like a fully fledged word-based LLM. But this allows you to really understand everything from scratch, and you can run it on a very small GPU. So it doesn't require a huge cluster and a lot of training data to see this working. So I really recommend this one. And the second one that I recommend is build a large language model from scratch. This is a book which is not even completed. It's currently being written by Sebastian Rashka, who is one of the best people out there pushing out very, very technical content on the foundations of deep learning and language models. So there are around 5 chapters ready, and this is a bit different than Karpathy's video because this is actually going to walk you through how to build essentially a version of the Llama language model, and it's going to be as big as Llama, and you're going to build every single component of it, every single decoder block, the attention mechanism exactly as it is in that model. So I really, really recommend this particular resource. So for the remainder of this episode, we are going to take a few open source language models and we're going to check them out, run them in our notebooks and see how they perform. First of all, as you can see here, we have a T4 GPU on Colab. These you can get on the free tier. And I've already started the notebook and installed our dependencies. In reality, what you need here, the most important thing is the Transformers library by Hugging Face that we've already used in the BERT episode. And we're going to take most of the models or all of the models from Hugging Face. You are going to need an access token because the two models that we're going to use, Google's Gemma and Meta's Llama, require you to essentially go on Hugging Face and accept the terms and conditions, and then immediately you do get access. So populate that variable with the token. So before you can run a model, of course you need to check that that model fits into the GPU that you've got available. So very simple way of checking this is to use this formula here. So let's imagine you have a language model which has 1 billion parameters. Okay, so each parameter is essentially a floating point number, 32 bits, and that's 4 bytes. So 1 billion weights, 1 billion parameters is going to be roughly 4 gigabytes. So you need to have that space in the GPU's memory. Now that's for inference. If you actually want to train that model, you need much more space. Rule of thumb is that you need 6 times the amount of space because you need space for each parameter additionally for the Adam optimizer, the gradients that you have to calculate. So all the derivatives that you calculate every time you do back propagation. And obviously you've got the activations and other temporary variables there. So roughly for 1 billion parameters, you are going to need a GPU or a set of GPUs that together give you 24 gigabytes of memory. And that starts to be quite a big number. And we are speaking about a 1 billion parameter model. Just to remind you from last episode, even smaller models by today's standard are still quite big. So GPT-3 is 175 billion parameters. So if you do the math in your mind, that's quite a lot. And when it comes to open source models, as we have seen, well, you can see here that some of them are around 7 billion or 2 billion parameters, and these sizes are kind of manageable on smaller GPUs. But then the majority of the state-of-the-art, even open source models are 70 billion parameters. So keep that in mind when you want to run these models. Now for this episode, we are going to run Gemma 2 billion parameters, which we're going to be able to easily fit in our T4 GPU. And then we're going to run, Llama-2 7 billion, but that wouldn't fit in our GPU, so we're going to quantize it. And I'll tell you a little bit more about quantization later. Now, to check how much memory is available in your GPU, you can use this NVIDIA tool. And as we can see here, we've got roughly 15 gigabytes of memory available. We haven't used any of it, so right now there is 0 megabytes used. But this will change in a second when we load the model. So let us start from Gemma. As I said, you're going to need to get access to this model, which is a gated model, by going on Hugging Face and accepting the conditions of use. Once you've done that, you are gonna load the tokenizer for the model, which has typically the same name as the model, and then you're gonna load the model itself. So this is gonna connect to Hugging Face servers, and it's going to download all the model's weights and load them onto our GPU. This is gonna take some time, so I'm gonna be back when this is done. Okay, as we can see, the model has finished loading, and we can check the memory of the GPU, and we are expecting around 8 to 9 gigabytes occupied, which is the case. By the way, there is another way of checking or estimating how much memory you need for a model. This is on Hugging Face. So you can essentially put a model name in there. So let's take, in this case, Gemma 2 billion. And we can calculate the memory usage. Now, it doesn't like this because, again, this is a gated model and you need to provide an access token. So I've actually pasted my access token in, and now I've removed it so I can show you the page for Gemma. And roughly this tells us that the total size of Gemma is going to be 9 gigabytes if we want to do inference, and if we want to train it using the Adam optimizer, that's what we are going to need in total. So again, even for a small or relatively small model like Gemma, training it is not going to be possible on a consumer GPU. Anyway, we've loaded the model and now we can take a look at it. And this is exactly what we're expecting. This is a decoder LLM. So you can see the different decoder blocks which are available in there, the embedding layer that we've discussed, and then the multi-layer perceptron after the decoder block and the normalization layer. So this is pretty much the same or very, very similar to the and any other decoder that we've seen. What changes is the number of layers and some of the details, the activations, and so on. Now, let's put this to the test. I will delete this for now because I want to show you that this model that we've just loaded, this is essentially just the base model. So this is the pre-trained model. It's not been fine-tuned for instructions or anything. It's just been trained on next word prediction on a large data set. So the only thing this model can actually do in this autoregressive fashion is to predict the next word. So if we take a Wikipedia article, for example, say Back to the Future, I can take the beginning of this article, put it in here. So obviously this is an unfinished sentence. So I'm going to tokenize this input as we would do with any model. And then I'm going to pass the input tokens to the model to then generate a maximum of 100 tokens. And as usual, we've already seen this, but we can pass a temperature, top K and top P. And if you don't remember what those are, we looked at those in the language modeling episode. I'm just going to bring them up on screen again. So they basically control how we sample at each step from that probability distribution. And specifically the temperature decides or changes how peaked that probability distribution is. A colder temperature or a cooler temperature means that we get more predictable answers. A higher temperature, we get more variable and creative answers. Anyway, this is done. And you can see that the output, if you ignore the warnings, obviously it tried to complete this. Film directed by Robert Zemeckis and written by Bob Gale. This is effectively true. The film stars Michael J. Fox, Leah Thompson. It's actually quite similar to the, as expected, to this particular entry in Wikipedia. This was part of the training set, and this is just completing it in a way that's statistically meaningful to the training set that is. So obviously it's not exactly the same. You can see it says it is the first installment in the Back to the Future film series. I do not think that it says this here, but obviously it knows a lot about that, and it keeps going. The film follows Marty McFly, a teenager, yada, 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 and it stops because we've reached the 100 tokens. Now, that's what a model trained on next word prediction actually does. But I can change this, and I could say, for example, back to Tiramisu Land, which happens to be tiramisu, my favorite dessert, and I could say 2080 Italian science fiction film directed by Donato, and I can run this model. And what it is going to do, it's going to look at those tokens and it's going to try to complete this in a meaningful way. So let's see what it comes up with. So Back to the Tiramisu Land is a 2080 Italian science fiction film directed by Donato and directed by Donato Carrisi. So that's a real name of a writer in Italy, and I think because I have the name Donato here, it kind of made sense in the probability distribution to pick something that was related to Donato. The film is a sequel to the 2013 film Back to Tiramisu. Again, it's completely hallucinating this. It's not reasoning. It's just completing a document in a way that makes sense. And that's what it's doing. Then it's even generating some HTML, and so on. So this is what a language model actually does. Next word prediction. But as we said, the interesting part of GPT models is that at one point, as they are doing this next word prediction, they show emergent abilities. So just from this pre-training, without any fine-tuning, they seem to be able to sometimes do tasks like translation, question answering, and so on. Let's put this to the test. So again, this is the same Gemma-based model, and I can say maybe let's try. Actually, I've got it down here. So, for example, I can say English, hello, Italian, What I am expecting here is that the likely completion is going to be ciao. Indeed, it added a space, which made sense after the colon, and then ciao, which is the translation of that. And then continued. Again, remember, we've asked 50 tokens, and he kept predicting. And then he says Spanish, hola, French, bonjour, and so on. So it's kind of doing this thing. And you can imagine, again, intuitively, that it's able to do this because it makes sense based on the stuff that was in the pre-training unsupervised data set. We could do something else. This is, by the way, if you recall, this is a zero-shot task. So we've just asked it to do something and it's done it. We could show it one example exactly of what we do or what we want. So let's try this. English, hello, Italian, ciao, new line, which is going to be something meaningful in the pre-training set that it said. And then I can say English, I love you, comma, Italian. And let's see if this is able to do it. And it actually did it. So it completed ti amo. But then again, what is important to understand is that the model keeps going. English, I miss you. Italian, mi manco, which, by the way, is not the correct translation of I miss you. I'm sorry, mi scusi, and so on. So that's what the model does. That's the emergent ability. Now, where I want to go, I want to jump to the instruction fine-tuned version of the base model. Now, remember, instruction fine-tuning is where we want to harness this emergent ability of the model and fine-tune it on this set of prompt and completions, which are responses for the prompt, so that the model learns to respond to our questions better. So the way that we typically would do this, we would have a training set with a lot of examples, typically written by humans. And I've got one here, which is quite large. It's the Evolve Instruct dataset, 196,000 entries in here. And for example, we can see these entries. And again, I should say these entries are either written by humans or derived from content which is written by humans to teach the model how to answer, what's the structure of a prompt or a question and how to answer it. So let's take a look here. So for example, we have a prompt, please develop a Python program that generates a list of prime numbers, yada, yada, yada. And then there is the response from GPT. Let me see if I can make this a bit larger. And this is a potential response that we want the model to learn to produce. Here is a Python program, and that is the program. So imagine now the model that we saw before fine-tuned on a similar data set. And that's what Gemma 2B-IT is. The IT means instruction fine-tuned. You can actually take a look at the model card here on Hugging Face, and obviously there is a 7 billion version. So we can load this model. Now, before we load the model, we need to restart our environment because we need to free up the memory of the GPU. And after the environment has restarted, we are going to need to rerun this cell to install the dependency and set the access token. So I'm going to do this and be back in a second. So we restarted the notebook, we rerun this cell, and now we can jump to loading the instruction fine-tuned version of Gemma. Exactly as before, we just have to change the model name, and now it's going to load the instruction fine-tuned version. So the model is loaded, and now we can use it exactly as before. So we can put an instruction in there and see how the model does. In this case, explain how a neural network works. And it comes back with a pretty reasonable answer. A neural network is a computational model inspired by the structure and function of the human brain, and so on. So that's a pretty good answer. And as you can see, when it's done, it also produces an end of string token, which probably happens before the max length. So this fine-tuned model also knows when to stop, and it's likely to produce the end of string token. Whereas the previous model, if you remember, just went on generating things until it reached the maximum number of tokens, because it's not been fine-tuned to really give an answer. It's just completing and keeps completing everything until its full context size if we don't stop it. Now, let's try this and see what happens. So where is it? So again, this is not properly an instruction, but you can see that in this case, the model replies, the correct answer is Italian ti amo, which is kind of like, okay, yeah, the answer to English I love you, the correct answer is Italian ti amo, but you can see that you really didn't understand the task very well. Probably if we asked the task in a more natural way, it would have understood it better. But anyway, you can see that it's trying to explain things. Ti amo is the correct translation of I love you in Italian, and then it puts the end of string. It is still more coherent than what we got before. And again, we can try something completely different. I don't know if Gemma 2 is going to be able to do this, but write a Python script that prints I love you. Let's see if it's able to do this. Okay, that's pretty good actually. Beginning of string, that's what I provided. And then it's interesting because it completed it with to the user, which is not part of my prompt, but then it obviously added like the correct Python and even an explanation in Markdown. So it means that the data set that's been used to fine-tune Gemma, in the completions, it had a lot of examples that had this particular structure. Okay, this is how the code works. That's the format that I'm going to use to show the code. And then this is the explanation and so on. Now, furthermore, as we saw in the episode, during fine-tuning, you also try to give the model a little bit of structure. So some models, or the prompts, a little bit of structure. Some models wrap the instructions in some special tokens, instruct, for example. But for Gemma, what they did, which I have here as well, they specifically fine-tuned the model for chat, dialogue, for conversation. So it learns the turns. So they have special tokens for the start and the end of a turn, and for two different roles, the user and the model itself. And this will improve how the model interacts. Now let's see how we can use this. So we could go back here and just use all of these, start of turn, user, and then we'd have a new line and so on, and then we'd put end of turn. But we can do this much better using the Hugging Face tokenizer object, which already has a template specific to the model to create chats. So we can basically pass an object with the role, user, and the content, and then we can ask the tokenizer to apply the chat template. And again, the chat template is going to be whatever the model creator have used during the fine-tuning. So if I do this, I am going to get this format here. So start of turn, user, new line, explain, end of turn, new line, start of turn, model, new line. And so if I pass this to the model, now because it's seen a lot of examples of these in the training set, it should be able to answer following that format. So let's tokenize this and pass it to the model. And you can see the completion. A neural network is a computational model inspired by the structure, yada, yada, yada. And we can probably do a lot of other things. Remember, we could also create a memory of a conversation. So in this case, I would have as the role the model, and let's say that the model answered this. And then I could have another turn for the user, maybe asking a follow-up question. Let's see. In which way is it inspired by the human brain? So we get this prompt with all of the delimiters added. And again, this should facilitate that answer. Neural networks are inspired by the structure and function of the human brain, particularly in their hierarchical organization of interconnectedness of its neurons. End of string. Okay, now I want to show you another model, Llama. If you remember, and of course you probably already know, Llama-2 is one of the best open source models available. Very soon, actually, we are going to have a release of Llama-3 that Meta has been working on. But what I want to show you is how we can load the base Llama-2 model, which is 7 billion parameters, in our GPU, which is, again, quite a small GPU with only 15 gigabytes of memory, how we can load a larger model that wouldn't fit in there by quantizing it. So let's jump to the quantization. Now, quantization is a technique whereby you take that full precision weight, which we said is 32 bits, and you project it into a lower precision number. So for example, you can project it into a 16-bit floating point value, but you can also project it to an 8-bit and even a 4-bit integer. So of course, in that process, you lose some of the precision, but empirically, we see that models still somewhat perform. And of course, although you do lose some of the performance, you still get something out of these. What we're going to do is int for quantization, so 4 bits, and that's very, very simple with Hugging Face. So the way you do this, you load the model, Llama-2 7 billion. The HF here is means Hugging Face format. And by the way, you can find the model card on Hugging Face. I don't think I have the link here, but let's check that model. Llama-2 7 billion Hugging Face, and again it's a gated model. So I am now going to load this model, and this is the bit that's gonna quantize it for us, and we're gonna check it out. Alright, the model has loaded. Of course it took more time, it's a much larger model to download. But if we go and take a look at the memory utilized in the GPU, you will see that this only takes 4 gigabytes, because after we downloaded it, again, we've done this quantization. So we've taken each 32-bit weight and we've projected it into a 4-bit integer. So we can fit it very nicely in our GPU. So let's try to use the model. Again, as I said before, we could feed it a Wikipedia article or the start of anything. It could be a book. For example, once upon a time, a princess lived in, and let's see what it generates. But obviously it has seen in its training set a lot of fairy tales. So we know what it's going to do. It's going to come up with something which is statistically significant. And there it is. Once upon a time, a princess lived in a castle in the middle of a field. Hopefully the princess was not a witch, but if she was a very good witch, and so on. So that's the model. We can try one-shot learning or one-shot tasks. For example, English, hello, Italian, and see if this works. I expect Llama, similarly to Gemma, the base model, to be able to do this. And it does something very similar to what Gemma has done. These models are pre-trained on quite similar data sets, especially data sets that come from the internet. We saw Common Crawl, for example. But anyway, it can actually perform the task. And again, it then continues hallucinating all of these. And then it repeats this English, hello, Italian. So kind of a little bit random. And again, if we wanted to do few shot learning, we would provide an example and then we would ask for another word, for example, glass, Italian, and I'm expecting that this should know that bicchiere or vetro is the correct translation. Indeed it is. But again, as we saw before, this doesn't really know when to stop. It's kind of not really executing the task per se. It just keeps going, and at some point it kind of like pops out with a Spanish version. I don't even know if this is correct. But again, as we did for Gemma, we have an instruction fine-tuned version of Llama called Llama-2 Chat on Hugging Face, and so we can try to load that version and see how the instruction fine-tuned version behaves. The only thing that we need to change here and here is that we are adding chat. And again, this is the quantized version. I will not restart my NVIDIA card because I've already got, I think, quite a lot of I've still got quite a lot of space in here, so I should have 4 more gigabytes to load this particular model, and then we are going to play with it. Again, it's gonna take quite some time the model is fairly big. And while the model is loading, we can go back to the Hugging Face memory calculator to see how much space we would actually need for Llama-2 7 billion if we were not quantizing it. And that's quite a lot of space, 25 gigabytes just for the inference. And if we wanted to train this model with all the additional space, obviously we would need more than a single large GPU. But again, the quantized version is gonna fit into 4 gigabytes, and it is still loading here. Okay, this model has now loaded, so we can try what we had before and see how the model behaves. That's just this kind of 1 or 0 shot learning or completion. It does pretty much what it did before, but here we can give it an instruction. That's a instruction tuned model, and if I'm not mistaken, this is how you would do it in Llama-2. You'd have these instruct tokens there, and then you would give your instruction, translate I love you into Italian, and I do expect that the model is actually going to be able to do this fairly well. I mean, this is a quantized version, but it did work. It replied, sure, I love you in Italian is ti amo. Here are a few more ways to express love in Italian, and these are absolutely fantastic. Now, if we remove the instruct delimiters for the instruction, the model might not perform as well, because it might not really understand where the instruction starts and stops and how to complete it. But let's give it a go. Aha, this is it. This is what I wrote, and that's what the model completed. Space, everybody wants to express their love to their beloved ones, right? So if you want to say I love you in Italian, you can use one of these phrases. Amo te. This is the most common way to say I love you in Italian. That is not really true. So actually, the performance, even a fine-tuned model, if you're not going to use the correct way of prompting it, that you're going to need to look up in the documentation of the model, even the instruction fine-tuned model is actually not going to perform well. Let's try one more task. Write a program in Python to sort a list of names and there it is. Sure. Here is a simple program in Python that sorts a list of names using this sort method, and it's correctly surrounded by the code blocks. It's got sample names, yada yada yada, and it didn't finish because again it reached the max length. And as a final test, just to make this point clear that it's important to know how the model has been trained, if we remove those tokens that the model saw during the instruction fine-tuning, and we just give the instruction, it's likely that the model is not going to perform well. And look at what it completed. Here is a list of names. I didn't ask for a list of names. Write a program in Python to sort. Aha! Look at this. So this is another instruction. So it's completed that instruction with some other instructions. There is a hint. You can use the built-in sorted function. So you can see that this is not actually doing what we asked. It's just completing with stuff that it's seen in the data set.